Hello everybody, this is Suvarshila working as an Associate Professor, Department of Computer Science and Engineering at Institute of Aeronautical Engineering. In this video, I would like to discuss about bi-connected components at articulation point and how to find articulation point, what is the reason or what are the reasons to identify these articulation points, its applications. So, this is a part of the lecture related to graph algorithms. So, this video includes basic graph definitions. We will just review the base graph definitions. Then how to construct a DFS and BFS spanning tree briefly. Connected components, bi-connected components, and what is an articulation point, how to find the articulation point. So, as we are aware of that, a graph is defined as a pair of sets, two sets, G of V comma E. V is a set of vertices, it is non-empty set, and E is a set of edges, possibly it may be empty set also. So, in a graph, edges will be there. Each edge is going to be represented as a Vi comma Vj, that is an edge between Vi to Vj. In case of undirected graph, these pair of vertices are going to be considered as an unordered pair, and in case of directed graph, the vertices are considered as an ordered pair. So, in case of undirected graph, we will have V0 V1 is equal to V1 V0, but in case of undirected graph, V0 V1 not equal to V1 V0. In case of directed graphs, from where that particular edge initiates, we will call it as a tail, and towards which vertex it is moving, that is called as a head. Sometimes we will use these terminology also. So, if edge is an ordered pair, then we will consider it as a directed graph, U to V. Diagrammatically, we will represent by an arrow mark towards the head. And if graph is undirected, then the edges are going to be unordered pairs. So, what is a complete graph? A complete graph is a graph that has maximum number of edges. That means, in other words, we can say between each pair of vertices, if an edge is there, then we can consider it as a complete graph. In case of undirected graph of n vertices, the maximum number of edges will be n into n minus 1 by 2. If it is undirected graph. If it is a directed graph, no division of 2. So, that's why we n into n by n minus 1. That means in a directed graph, n into n minus 1. In undirected graph, n into n minus 1 by 2, because same edge is going to be considered as a uv is equal to vu also, no? So, that's why half of the edges are going to be considered as a maximum number of edges to form a complete graph actually. So, in this example, G1, you have observed, G1 is a complete graph. If you find between any pair of vertices, there is a direct edge. So, every pair of vertices has a direct edge, then we will call it as a complete graph. What is the set of vertices? 0, 1, 2, 3 is the set of vertices. Set of edges are 0, 1, 0, 2, 1, 1, 0 and 1, 3, 2, 3, 2, 0, 2, 1. Like that, every pair is having some edges. So, if you consider these edges here, how many edges are there? Vertices are 4. So, 4 into 4 minus 1 by 2, that is 12 by 2, 6 vertices, because it is a undirected graph. So, 6 vertices are there, then we can say it is an undirected graph. Now, G2 and if you are considering G2 and G3 in these two diagrams, these are considered as a not complete graph, incomplete graphs we can say. In other words, why incomplete means there are some vertices between which there is no direct edge. There are some vertices between which there is no direct edge. For example, in this second graph, between 3, 4, no direct edge. Between 5, 6, no direct edge. Between 5, 0, no direct edge. Between 4, 0, no direct edge. So that's why it is an incomplete graph. This is incomplete undirected graph. Even coming to the G3, it is a directed graph. Even though it is a directed graph, it is incomplete. Why? Because 0 to 1 path edge is there. 1 to 0 is also an edge is there. But coming to the 2, again we should have an edge. 1 to 0 is there, 1 to 2 is there. But 0 to 1 is there, 0 to 2 is not there. And 2 to 1 is also not there. So that's why some edges are missing here. So we can consider it as an incomplete. So if a directed graph doesn't have maximum number of edges, we can consider it as an incomplete graph. Even in undirected graph also, if the number of edges are less than the maximum number of edges, possible edges, it is an incomplete graph. So when we are considering this an edge, we will use generally the terminology as adjacent and incident. Adjacent means side. So if there is an edge between two vertices V0 and V1, then in an undirected graph, if it is undirected graph, V0 and V1 are termed as adjacent vertices. So that's why we will use to represent a graph also adjacency matrix. That is, those who are connected directly, those are going to be considered as adjacent vertices. That means the edge V0, V1 is incident on vertices V0 and V1. Because there is no direction, no incident to, incident on is not there. So it is undirected. So that's why it is incident on V0, V1. For example, if you are going to consider in a directed edge V0 to V1. So directed edge is an ordered pair. So it is represented, just representation is also slightly different. In a directed graph, V0 is known as, because from V0 to V1. So V0 is an adjacent to V1. Or we can say, in other words, V1 is adjacent from V0 because it is having a node edge V0 to V1. So the edge V0 to V1 means it is starting from V0 towards V1. So V0 is adjacent to V1 and V1 is adjacent from, because it is starting from V0 to V1. Similarly, incident also, the edge V0 V1 is incident on V0 starting from V0, no, that's why. And it is V0 and V1, it is incident on, you can say. So in a graph, again, we will identify what is subgraph, what is a path, and what is the length of the path. Subgraph of a graph G is another graph, it is represented by G dash, in which the set of vertices are subset of the vertices of main graph. Similarly, edges are the subset of the edges of the main graph. So, for example, if you are going to consider V of G and G dash are two graphs where G dash is a subgraph of G, then vertices of G dash is subset of V of G. Similarly, edges of G dash, E of G dash is a subset of E of G. What is a path? Path means from a vertex VP to vertex VQ in a graph, there is a sequence of vertices must be there in between. Then we can say it is a path continuously. Right? So that means, for example, VP, VA1, VA2, etc., VAN, VQ. There should be an edge between two consecutive edges. That means the edges must be continuous. Then we can say it is a path. That means VP to VA1, one edge, VA1 to VA2, VA2 to VA3, etc. So on and so forth. Similarly, even if the path can be identified even either directed graph or undirected graph. If it is a directed graph, the path must from a particular vertex to a particular vertex means in between also edges must be toward that vertex only. The length of the path. Length of the path means number of edges in that particular path is known as length of the graph path. For example, if you consider this G1, and when we are having this G1, you can have multiple subgraphs. For example, this is only one vertex, no edges. This is also subgraph. 0, 1, 2 are subset of V, as well as 0, 1, 0, 2 are the subset of vertices. And so on and so forth. All these are subgraphs. Similarly, subgraphs, if you even directed graph also subgraphs 0 or 0 to 1 only one subgraph, 0 to 1, 1 to 2 is another subgraph, and 0 to 1 and 1 to 0 is also there, then this is another subgraph. That means it is incident from all. These are all subgraphs. When you are going to consider the path, for example, I like to take a path from in G1, 1 to 2, vertex 1 to vertex 2 path. What are the edges? You can say 1, 0 and 0, 2. Direct edge is also there. Without direct edge also you can consider. Or I'll consider this directed graph. Then you will maybe understanding. From 0 to 2 path. 0 to 1 is one edge, 1 to 2 is another edge. Then this is known as path. What is path length? 2 edges are included. So path length is 2. So a graph with feedback loops and multi-graph. Self loops will be there, or we will call it as a sometimes multiple edges will be there. Self edges means starting from the vertex reaching to the same vertex. That is, your edge is 0, 0, 1, 1, 2, 2, etc. Sometimes it happens from its place to its place. Some self loops may be there in your graph if necessary. Similarly, multiple edges. Multiple edges means between two vertices, multiple edges are there. We will call it as a multi-graph. If you observe here B, between 2 and 3, 3 edges are there. Between 1 and 3, 2 edges are there. Sometimes it happens when we are going to consider specifically weighted graphs. The edge, first edge and the second edge weights may be different. Their significance is going to be considerable by us. So, proper graphs and subgraphs. Subgraph already we defined. Then what is a proper graph means? A proper graph is a graph. There is no loops, there is no multi-edges. I explained what is a loop here. For example, here it is loop and these are multi-edges. So, there is no loop means no self edges will be there. Similarly, multiple edges between pair of vertices should not exist. Then we will call it as a proper graph. And we defined already subgraph, subset of vertices of subgraph are subset of the main graph vertices, and edges are subset of the main graph edges. Now we'll consider simple path and I explained to you already path. Simple path is a path in which all vertices at the first except the first and last vertices possibly are distinct. Cycle means the first and last vert. It is a simple path, but the first and last vertices must be the same. Must be the same. Then it forms a cycle. For example, if you are going to consider 1 to 1, a cycle is there. How? 1 to 0, 0 to 2, 2 to 3, and 3 to 1. So these are the path is having 1, 0, 2, 3, 1. First one, last one are going to be the same. It forms a cycle. So we will consider this path which starts and ends with the same vertex is a cycle. In an undirected graph, two vertices V0, V1 are connected if there is a path in G from V0 to V1. So now we are moving to our basis of our main discussion related to the components. So that's why bi-connected and connected components. So what is connectedness? First we will define. In an undirected graph G, two vertices are going to be connected if there is a path from vertex 1 to vertex 2 or vice versa, because undirected no problem to us. But that means two vertices, they may not be there need not be any direct edge, but if they have a path from one reachability, in other words we will call it as. So if you are able to reach from one source vertex to any destination vertex, that path exists, so that's why we will call it as a connected. Those two vertices are connected. No need to have any direct edge. If direct edges, it's well and good. Even if it doesn't exist also, if you're able to reachable to that one, then you can consider it as a reachability is possible. It is connected. Coming to the graph, because we defined only and two vertices are connected. When will you say a graph is connected? If for every pair of distinct vertices Vi and Vj, if there is a path from Vi to Vj, every, already I defined what is connectedness. Connected means each pair of vertices, if there is a path, then you can say connected. That means from any vertex, if you are reachable to all other vertices of the graph, from each vertex to all other vertices of the graph, reachability is there. We can say that that particular graph is connected. So there is a difference between complete graph and connected graph. Remember that in case of complete graph, between each pair of vertices, an edge must be there. In connectedness, graph connectedness means between each pair of vertices, there must be a path. Need not be edge, path. Reachability is enough for us now. If you consider these two examples, connectedness and here, the first one is connected graph, connected even zero, between any pair of vertices, path is also exists. Of course, direct, complete also. Complete means automatically it is connected only. So, acyclic graph is a tree is known as acyclic graph. Why? Because tree is a special case of graph only. So, tree is a hierarchical structure. From a graph, a tree can be generated which doesn't have a cycles. So, tree can be termed as a acyclic graph. So, now we defined connected edge or connected vertices and connected graph. Then what is connected component? The connected component of a undirected graph is maximal connected subgraph. So, maximal connected subgraph means the number of components are going to be connected components of the graph is greater than or equal to 2. That means if you are able to generate connected components of a graph more than 2 components are equal to 2 components, then you can say it is a connected component. A tree is a graph that is connected and acyclic because in a tree, all of us aware of that. From any node, we can reach to the all its other nodes. Because undirected, you can go back and you can traverse. And what is strongly connected? A directed graph is strongly connected if there is a directed path from Vi to Vj and also from Vj to Vi. If there is a path between two pair of vertices starting Vi to Vj as well as Vj to Vi, then we can say that the graph is a strongly connected graph. In a directed graph, there is a path between every pair of vertices. That too Vi to Vj is there means Vj to Vi also must be there. Because it's a directed, then we will call it as a strongly connected. What is strongly connected component? Strongly connected component is maximal subgraph that is strongly connected. If you observe, this is the example. This is not strongly connected. Why not strongly connected? Because the components which are going to be generated may not be having direct paths. You observe here, 0 to 2 is a path, 0, 1, 1, 2. But 2 to 0 is no path. From 2 to 0, no path. 2 to 1, no path. So that's why it's not strongly connected graph. But we can generate strongly connected components. If you observe these two components we are generating, one is 0, 1, that is two subgraphs or connected components we are generating. One is having two vertices 0, 1. So 0 to 1, one edge, 1 to 0 is there. Second one is only a single vertex. So these two are strongly, we have components of our graph. Those are connected components, that is connected subgraphs are available. More than two components we able to decompose now. So then we can call it as a maximal strongly connected subgraphs. So a graph with two connected components, with two or more connected components will be considered as a maximal connected components. For example, if you consider this is a graph, the entire graph. Is G4 is connected? No. Graph G4 is not connected. Why? Why? Because there is no path between 1 to 5. There is no path between 1 to 4, 1 to 6, 1 to 7 or other way also. Because connectedness means from between each pair of graph, there must be a path. Because these two subcomponents are there. If you observe this graph is having two components. H1 is one component, H2 is another component. Independently connected components are there. Individually, these components are connected. But as a graph, I am considering because these two are two separate components. No, so there is any connection between these two components. That's why each pair of vertices doesn't have any path. But individually, these components are known as connected because in these components, from each node of this component to other nodes of the same component are reachability is there. 0 to 1 you can move, 0 to 3 you can move. How can you move? Either through 1 or 2 or 0 to 2 is there. Similarly, 1 to 0 is there, 1 to 3 is there, 1 to 2 like that. These two subgraphs are going to be considered as a maximal connected subgraphs because it is having two connected components. G4 is not connected originally, but it has two connected components actually. So that's why, in summary, if G is connected, if there is a path between each pair of vertices, otherwise G has greater than or equal to two connected components, then we will call G as a maximal connected subgraphs. So G is, in the previous example, here G has not connected, but it is having two components, connected components. So that's why maximal connected subgraphs are there. We will call it as a maximal connected subgraphs. Now coming to the degree of the vertex, all these are basics. The degree of vertex is the number of edges incident from the vertex or to the vertex. So if in case of directed graph, we will have in degree and out degree. In degree means the vertex V is the number of edges. That means in degree means vertex V is the number of edges that have V as the head. Coming from some other vertex towards here, we will call it as the in degree. Coming towards the vertex. Moving from the vertex, we will call it as the out degree. But in case of our normal undirected graphs, there is no direction, no. So that's why number of edges incident on that particular vertex can be the degree of the vertex. So dA is the degree of the vertex. I in the graph G with n vertices and e edges. The number of edges are going to be sigma 0 to n minus 1 dA by 2. For example, undirected graph, if you consider 0, how many edges are? What is degree of 0? 3. You observe 3 edges are there, right? So all vertices are having 3. From each vertex, 3 edges are connected. Coming to this tree, 0th vertex, 2 edges. First vertex, 3 edges. You observe 3, 4 and 0 also connected. 3, 2 also 3. 5 and 6 and 4 are 1, 1, 1 only. Because 3 is connected to 1, 4 is connected to 1 and so on and so forth. If these two are undirected. If you come to the particular directed graph, now for each vertex we will have in degree and out degree. You consider 0. How many edges are coming towards 0? Only 1. So in is 1. How many edges are going from 0? 0th vertex 1. In is 1, out is 1. Consider 1, vertex 1. In vertex 1, how many edges are coming towards 1? Only 1 vertex. This is 0 to 1. So 1 is in degree. How many vertices are going from vertex 1? It is moving 1 edge is towards 0 and 1 edge is towards 2. So out degree is 2. Coming to the 2, in degree is 1 and out degree is 0 because from 2 there are no any edges are moving from. So graphs are represented, already we discussed adjacency matrix, adjacency list and adjacency multi-list. This is adjacency graph representation. So in which we are representing a matrix of n by n, where n is the number of vertices. If there is an edge, we are representing the respective position, ij position, as a vi to vj. Any edge is there, vi vj location will be 1. Otherwise, the respective location is 0. So generally, whenever we are executing or running the programs related to the graph, if we are representing a graph by using our adjacency matrix, then the complexity will be n square minimum, because a matrix we are going to use, no, so we have to access the matrix, adjacency matrix of order any n by n. Matrix means 2 dimensions, n square will be there in general. Of course, may be added further, that is different issue depending upon the complexity of the other logic. Similarly, if you are going to represent by using adjacency list, this is a linked list representation. These are shown to you now. Now, directed or undirected graph can be considered. Edges are represented as a collection of lists actually. From each vertex, and what are the adjacency vertices are there, and those are forming a list actually. If we are using this adjacency list as one of the representation techniques or implementation of graph in our real-time applications, the complexity will be order of edges, number of edges e. Similarly, multi-list can be considered. From each vertex, for all other vertices, the edges are going to be represented. Various operations are going to be performed on graph. Traversal operations, as we discussed earlier videos, depth first search or depth first traversal and breadth first traversal. This depth first traversal is going to be considered as a pre-ordered tree traversal. Similar to that, breadth first traversal is level order, level by level, breadth, no, that's why. And the connected components are going to be defined. So based upon the connected components, we supposed to check whether our graph can be divided based upon a particular vertex as components of the connected components of the graph. And we'll discuss briefly about spanning trees. Spanning tree means a tree generated from the graph having all vertices of the original graph, but edges are going to be subset of the edges. That means a spanning tree can also be considered as a subgraph. So all vertices, but only restriction, it's not subset of vertices. All vertices of the graph must be included in our tree, but edges need not be included all, because it's a tree, no, we have to avoid cycles. So a spanning tree can be generated by using various techniques. We'll discuss next video about the spanning trees, but currently just to observe, we can generate a spanning tree by using either depth first search or a depth first traversal, or depth first traversal or a depth first search. If we generate a spanning tree by using depth first traversal, we will call the respective spanning tree as a DFS tree, depth first spanning tree. If you are going to generate a spanning tree by using breadth first logic, traversal logic, then we will consider that tree as a breadth first spanning tree. That means while adding non-tree edge into any spanning tree, if it creates a cycle, it's not a spanning tree. We have to avoid those things. I'll just briefly explain, because this is going to be used in our articulation point further. So DFS and BFS, this is the original graph. So first we'll depth first. Depth first means first we'll consider the source, all its children. Again from each child, all its children, and so on and so forth. So first 7 is connected, all its children means 6, 5, 4, 3 are connected. Then I supposed to consider 6, the first child. What are the children of 6? 6 is having 2 and 6 is having children 7. 7 is already included. So 6 is having 2, 2 is 1 edge is added. Right? So when we are going to consider these kind of spanning trees, DFS, depth first means level by level it is considered. But while adding any edge, there should not form a cycle. We supposed to remember. Similarly, of course, this red color is only non-tree edge we are going to consider, because already it is there, no, 5 to 6, that's why. So from 5 again I'll consider, because it is having 3, 4, 5, 6. If you consider, then 2, from 5 I can 2. Again 2 is having 2 children, 6 from 1 to 0, and so on. So BFS, if you are going to consider breadth first, that means depth first means if I am starting from 0, so 0 to 1, 1 to 3, and 3 to 7. Next, it will go to 7 to 4. But 4 to 1 cannot be added. So it will come back. Then it will add the next child, 5. And 5 to 2 will be there. And it will, 2 to 6 is added. Then there is 7 cannot be added because it is forms a cycle. Then we will go back. By this time, all vertices are included. Then you can stop. If you are going to consider depth-wise, till there is no further edges can be added. By adding an edge, it forms a cycle, we will stop. Coming to the breadth first, so we are starting from 0. 0 is connected to 1 to first level. Again, children of 1 must be considered, that is 3, 4. Okay. Then children of 2 must be considered, 5, 6. First level is completed. First 0th level completed. First level. First children of first node, children of second node are added. While adding every time, again we have to check the cycle process. Then I have to check children of 3, 7. Okay. And by this time all nodes are added, then we can stop. This is one of the BFS spanning tree, DFS spanning tree. We will get multiple spanning trees actually, depending upon the way we are traversing, depending upon the way we are choosing the starting node. So what is spanning tree based upon this concept? A spanning tree is a subgraph, minimal subgraph. Minimal subgraph G dash of G such that V of G dash is equal to V of G. Vertices are going to be included, all vertices. And G dash is connected acyclic. G dash is connected and acyclic, no cycles. So any connected graph with n vertices must have at least n minus 1 edges, no? We already defined. So any connected graph with n vertices will have n minus 1 edges. So that's why a spanning tree should include n minus 1 minimum edges. So what is a biconnected graph? A biconnected graph is a connected graph that has no articulation point. So we defined a connected component. What is biconnected component? There is no articulation point. We will call it as a biconnected graph. So what is meant by articulation point? Articulation point means here any vertex of G whose removal results graph disconnected. Otherwise, whose removal results components of the graph. So for example, if this is it this connected graph? Yes, currently it is connected graph, because from any vertex you can move to any other vertex. For example, I am removing 3. Removal of one vertex. If I am removing 3, what happens? So if you remove 3, then this is going to be connected here, and we are having 2 different components. 2 connected components we got. That means removal of a vertex making our graph into connected. Such vertex is known as a articulation point. Such vertex is known as articulation points. Of course, more are there. You observe here, you can remove 5. 5 is also an articulation point. Why? When we are removing 5, then what happens? This is removed. So this is one connected component, and this is a component, this is another. 3 components are there. Right? So when we are going to remove 1 also, it will get as a connected component. That means here, these from any connected graph, any vertex is removed if it results more than connected graph components, more than connected components, more than one connected component, we can say that respective vertex is known as articulation point. Why we need to discuss about this articulation point? This articulation point, for example, if you have, let us assume that this graph represents some network related to either, let us assume that electrical networks. From each node to other node, the connections are made, or waterworks, or any traversal process, that is road or transportation. So, if any one of them is removing or any problem occurs, for example, at this node a problem occurred, then what happens? There is no communication, no? There is no, for example, 0 to 6 communication is going to be lost. And similarly, 2 to 9 communication lost, because of this it is divided completely two separate components, connected components. So that's why what happens in real-time applications, in multiple applications, the communication is going to be lost because of such type of junctions. In other words, we will call it as a articulation points. So whenever we are generating a tree, a graph or a network based upon graph, we will first search or check any articulation points exist or not. If any articulation points exist, then we will take care of that. Without that articulation point, or we have to make it as a single connected component. So what is bi-connected component? Bi-connected component means a connected under the graph, there is no articulation points, we will call it as a bi-connected component, bi-connected graph. That means we cannot able to disconnect because of the removal of one node, then we will call it as a bi-connected component. So a graph is bi-connected if it contains no articulation points. No articulation point means there is no further division of graph into connected components because of removal of any vertex. Two edges are going to be co-cyclic if they are equal, or if there is a simple cycle that contains both edges actually. This defines equivalence relations on the edges of the graph. So, graph is bi-connected, and bi-connected components of a graph are going to be considered here. If you observe here, then based upon a particular point, if you divide, then you will get bi-connected components. So what is bi-connected component? A graph is bi-connected if and only if it consists of a single bi-connected component. Single bi-connected. If you observe, this is not a bi-connected because we are going to able to divide here. No articulation point will be there. If you observe, this is a bi-connected, this is a bi-connected, this is a bi-connected component. So removal of vertex doesn't divide our graph further into connected components. So how to find? So we understand the purpose of articulation point checking, because any network design we are considering any network design, in that particular graph, if any articulation point is there, possibility of communication get disturbance of the communication if that particular articulation point node is getting disturbed or damaged or problem with that particular node, because communication is going to be breakdown. So into components. So that's why we would like to find out articulation point, and whenever real-time applications, a network is going to be designed, these articulation points must be eliminated. These articulation points must be eliminated so that our graph becomes a bi-connected graph. So a graph is known as bi-connected graph if there are no articulation points. Bi-connected graph design is most suitable for real-time network environment applications. Anything, town planning you take, road transportation, even road transportation, if a particular bridge is there, if it get damaged, there is no path between communication between this side and that side. So this articulation point is like that over here. So how to find out articulation point? To find out articulation point, we need to follow these following steps. First, from a graph, we have to construct a DFS spanning tree. That means we have to prepare a DFS spanning tree, means construct a DFS spanning tree. That's why I introduced what is DFS spanning tree. Using depth first traversal technique, a spanning tree must be generated. And while generating this spanning tree, right for each node, we will call it as a DFS order number. In which order the nodes are added, all those order numbers are going to be, or we will call it as a discovery time, or we will call it as a D also. So DFS number or a D value or a DFS order value or a discovery time will be written on each vertex. We will see one example also. The lowest discovery number reachable to each node by taking the back edge. So we have to find out after giving the DFS number, that is depth first traversal order number will be given. In which order we are adding nodes to that particular tree, we will give the order number. After that, we have to find lowest discovery number reachable to each node. We will call it as a low, or we will represent it as a by using L. So we will find out for each node what is its lowest discovery number reachable to that particular node by taking any back edge. What is a back edge means? Back edge are considered as edges which are not included while constructing a DFS tree, because inclusion of that particular tree forms a cycle. So that's why certain edges are not going to be included. No? So that's why back edges, the edges we will represent which are not included while constructing our DFS spanning tree, those edges are known as back edge. Through back edge, if you reachable to that particular node with the lowest discovery number, then we will, lowest discovery number means lowest our depth first traversal or order number, that will be known as lowest number. That means first we have to construct a spanning tree. Second, we have to write DFS order number. Third one, we have to find out lowest discovery number has to be found for each node. Then after that, we have to check each pair of vertices UV, that is each pair of vertices in our tree UV, where U is a parent and V is a child, whether this following condition satisfies or not. What is it? U is a parent and V. So the lowest value of a child is greater than or equal to the discovery number of the parent, then the parent is an articulation point. So the lowest value of child is greater than or equal to discovery number of parent, then that particular parent is an articulation point. This rule applicable to all nodes except root. Please observe. DFS spanning tree now we observed for a tree except root. All this rule is applicable to all nodes other than the root node. For root node, special rule is there. What is that? If the root is having multiple children, automatically it is an articulation point. We need not check at all. If the root has only one child, then it is not an articulation point. If root has multiple children, then it is an articulation point. So we'll do some example. This example I will work out. Then first we will take an example based upon the tree. Let us assume that my graph is having, let us assume that 1, this is my graph, 2, 3, 'll represent a small graph and I will work out. So I'll take 1, 2, 3, 4, 5, 6. Let us assume that this is my graph. So I'll explain all those 5 steps here. If you are going to take this graph and I have to construct a spanning tree, I am starting from DFS spanning tree. This is, so we'll write it as a DFS spanning tree. So I'll construct this DFS spanning tree. So what is this DFS spanning tree? I'm starting from 1. So 1 to 4. Okay. 4 to 3. 3 to 5. After 5, again we cannot go back. So that's why I'll go 5 to 3, I'll go the parent. Even from 3 also, then we have to consider its children. So we are 1, 4, 3, 5. From 5, again you are going to have 6. So 1, 4, 3, 5, 6. Again I cannot go 3. Why? Because it forms a cycle. So I'll go back to 5. 5 children are not 3 and 6. I'll go back to 3. From 3, 2. So this is my DFS spanning tree. Now I have to draw the back edges. What is a back edge? I defined the edges which are not included in my tree. Those are back edges. This is included. 1 to 4 included, right? 4 to 3 is included. 3 to 5 is included. 5 to 6 is included. 6 to 3 is not included because it is forming a cycle. So 6 to 3 is not included means we will consider here. So let us assume that I'll take 6 to 3 as a package. Six to 3 is a package. I'm representing with black color. 6 to 3 is a package. So now this is included. 3 to 2 is included. And 2 to 1 is not included because it forms a cycle. So 2 to 1 is also one package. These are the packages, black color. Hope you understand. First we are constructing a spanning tree. 1, 4, 3, 5, 6. 6, 3 not included. Why? Because 6, 3 includes means it becomes a cycle. So we go back to our parent. From 5, nothing is there. Again from 3, 2 is left over. So 3, 2 was included. And from 2, 2, 1 is not included because it forms a cycle. So now whichever the edges not included, those are included in our tree, DFS spanning tree as a back edge. It is reachability can be considered by us. Then we will now note down the respective DFS numbers. So what are the DFS numbers we are going to use? We will write those DFS numbers now. In which order the vertices are generated, those are DFS number. This is 1, this is 2, this is 3. I'm starting from 1, so that's why 4, 5. After 5, this is 6. These are the DFS numbers. In which order we added to our depth first spanning tree, those are DFS numbers actually. Now I will use a table here. So in the table we will write. So in the table I'll write 3 tables are generated, 3 columns, 3 rows are generated. 1, 2, 3, 4, 5, 6. This is first vertex, second, 3, 4, 5, 6. Okay. So I am representing a table having 6 columns. 1, 2, 3, 4, 5, 6. 1, 2. These are the vertices. And this is my vertex values. This is DFS number and this is low value. So what are the DFS numbers we identified? For 1, 1, for 4, 2, for 3, 3, for 5, 4, and for 6, 5, for 2, 6 DFS numbers. Based upon these DFS numbers, we will consider what are the low values. Low values means here reachability constraint is there. What is a low value? When we are going to consider low value means the discovery number which is the minimum DFS number reachable to that particular node. How to calculate this? For example, for each vertex, we would like to calculate low value of V must be calculated. So low value of V must be calculated means we will consider how to find out the low value of V. 3 components I'll take. One is minimum of, we have to consider this is, what is this? Minimum of first discovery number of, that is DFS number. DFS number of the vertex V. Okay. And minimum of DFS numbers of all its children. Any children are there, their respective DFS numbers, because through that also it can be reachable, no? So that's why DFS numbers of all its children. And the third one, most important, is and reachability. DFS number of back edge reachability. Okay, these three must be considered. So if another word you can consider, you observe here, low value is going to be having, these three are the low values. When we are considering this low value, low of u is equal to minimum of DFS number of u and minimum of low of w. W is child of u and minimum of DFS number of w are like that. UW is a back edge. So we have to consider all these three cases while calculating the low value. So how to calculate? First, I'll consider here low value of 1. So low value of 1 means, what are the first values? Low value of 1 means 1 is going to be having DFS number 1. Okay. So when we are going to consider low value of 1, 1 is having DFS number 1. And what are the children of 1? 4 is the child of 1. What is its DFS number? Minimum of all its children. That is only one child is there, 2. Next, back edge. So when you are going to consider this back edge, you are going to have the respective value is not going to be directly 4 inch. You cannot reach through back edge, no value. So 1, 2, minimum is 1. So lowest value is 1. Similarly, I'll consider lowest value of 2. So what is lowest value of 2? What is DFS number of 2? DFS number of 2 is 6. And all its children. No children are there. So none. And back edge. 2 to back edge is there. We are reachable to 1. No? So that's why back edge is to 1. What is the back edge? Vertex is 1. What is its DFS number? 1. Minimum of these two is 1. So DFS number of lower value of 2 is 1. I'll consider another one. Low value of 3. Low value of 3 means first what we supposed to consider? DFS of 3. DFS of 3 is 3. Children of 3. Children of 3 is having 2 children. And what are the children of 3? Children of 3 are having 5 and 2. 5 and 2 means 50 node DFS number is 4. Second node DFS number is 6. Minimum of these two. And back edge. From 3, through back edge is reachable. So how can you reachable here? Back edge is 3 to 2 and 1. So you reachable to 1, no? So that's why through back edge reachability is 1. So that's why 1. Minimum of these three will be 1 only. So low of 3 is 1. Similarly, low of 4. So similarly, if you consider low of 4 is equal to, what is low value of 4 is, you are going to have 2 is there here. And whenever you are going to have low of 4, the minimum value is going to be 1. If you calculate for that, we are going to get to 5. Low of 5 is 3 and the low of 6 is also 3. So this is the DFS number, this is the low value. These two must be found by us. So this is the first step. Then after that, we have to consider, so first tree must be drawn like this, back edges must be drawn, then edges are not included, so which we have drawn now. Based upon that, low value and DFS number must be calculated. Now I suppose to identify the articulation point. For each vertex, what are the vertices I have? 1, 4 I have vertex and I have 4, 3. These are the edges. 1, 4 is one edge, 4, 3 is another edge, 5, 6 is another edge, and 1, 4, 4, 3, 3, 5 is there. So 3, 5 is another edge, 5, 6 is another edge, and 3, 2 is another edge. These are the edges. 1, 4, 4, 3, 3, 5, 5, 6, 3, 2. So 5 edges are there. For each edge, I have to find out whether it is an articulation point is. What is articulation point? Means for each edge UV, I have to check if DFS number of, that means first what is the parent UV means? You have to consider, this is the formula we have to use. UV is an edge, U is a parent and V is a child. U is a parent and V is a child. So we have to consider UV and such that low value of V is greater than or equal to DFS number of U, then U is an articulation point. That is parent. Low value of child is greater than DFS number of parent, then parent is a articulation point. This we have to check for every node. For this node, I need not check. Why? Because parent is 1. What is 1? In my previous example, 1 is a root. If root is there, root cannot be an articulation point if it has only single child. How many children are there for my root? 1. Only one child, no articulation point. So this need not be considered. Why? Because 1 is a root with root with only one child. So this need not be considered. 4, 3. I will do one example. The remaining things you can consider. So if you consider 4, 3, I have to consider law of child means law of 3 greater than or equal to DFS number of 4. Law of 3 is equal to, in the previous slide we have law of 3 is 1 and greater than or equal to DFS number of 4 means DFS number of 4 is 2, which is not correct. So my 4 is not a articulation point. Now I will consider the next edge 3, 5. So when we are considering this 3, 5 as an edge, I have to consider law of child means law of 5 and greater than or equal to DFN of 5. Then DFN of parent. Law of child means 5. DFN of parent means 3. I have to check. Law of 5 is 3 and DFN of 3 is 3, then equal to satisfies. Then its parent is a articulation point. 3 is an articulation point for me. Similarly, if you consider for 5, 6 and 3, 2 also, this condition doesn't satisfy from the table if you just check. So in this example, we consider this articulation point is 3. If you observe our original graph, if this 3 is an articulation point, if you remove, this is divided into 2 components. So that's why we are going to consider 3 is an articulation point and we got through this process. So like this is the rule we are following. Similarly, one more example was explained to you and based upon which we can find out the articulation point. Once you find out what is an articulation point, we can use articulation point program so that we will avoid that articulation point while designing our graph. Okay, so by using this small program, we can identify DFS as well as articulation point and we can find out it. So thanks for watching this video and whichever examples are given in this, you can work it out on those examples also. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.